I'd like to preface this episode with a big shout out to my friend Martin Edwards, who helped me set up this studio. He gave me a lot of help and assistance in terms of lighting, camera angles, how to edit and so forth. So big thanks, Martin, appreciate it. Hi, and welcome to my series on production grade systems development. My name's Dave Oram, and I'll be your guide in today's episode where we cover telemetry. If you're new to this video series, I encourage you to go back, look at some of the earlier videos which give you some background leading up to this point. If you'd like to follow along in your browser, you can point it at github.com/davidoram/beaker. Otherwise, you can just watch me and I'll take you through the code on this video. Telemetry is a fancy word that just means measuring something and sending it somewhere for monitoring. Think of a hospital where you've got a heart monitor attached to a patient. It's sending a stream of data to the nursing stations. So it's a bit like that with our application. We want to be sure that at all times our application's online and responding correctly, in order that basically we can serve our customers well. Some systems define these requirements a bit more formally using something called a service level agreement, or an SLA. That might state the response times for an API. For example, 95% of responses must be within 100 milliseconds and 99% of them within a second, something like that. So we can use telemetry to measure and capture that particular metric and then grade our system against its requirement. Like a nurse monitoring the patient, we need that information available to be able to monitor the health of our system. Another thing that a heart monitor might do is it might trigger an alarm when the heart rate falls outside of the normal range. This alarm might be something audible, for example, designed to draw the attention quickly to an urgent problem. We can use that same technique when our systems start behaving outside of their normal bounds. So we're going to use a standard called OpenTelemetry. What that does is it allows us to write our code in a vendor-independent way and then choose from any number of vendors the one that might suit us best on price, usability, or other factors. Our architecture here is that we have the application sending telemetry information directly to the vendor. This is a little bit of a cheat on my behalf to keep things simple. In a real production environment, it's much more likely we'd send the telemetry to a piece of software called a collector or an agent. Our app would send its telemetry to the collector, which in turn will be configured to filter, aggregate, maybe apply some custom rules before sending the telemetry data onto the vendor. Right, so let's talk about the vendor I've chosen. We're going to sign up for NewRelic using the instructions provided on this page. NewRelic and other providers are very generous in that they provide a free account so we can do a little bit of testing, see how they work. Okay, a bit of preparation work first. So what I've done is I've signed up to NewRelic and then I've created an API key using this option here. Go down to the NewRelic homepage, into your username and then to API keys. And you can see I've created one here for the beaker system. And just be aware, when you create that, you'll need to copy it straight away because the values are no longer displayed once you've created them. Then, we've seen this pattern before, but I've gone back to my code space user secrets and I've added that NewRelic API key in as a user secret down here. Then when I restart my code space, that environment variable will be available and we use that to propagate the API key throughout the system. So before we integrate any telemetry code into the application, I'd like to show you what it looks like outside the application. There's a little tool called OTEL CLI that we can use to create telemetry information just from the command line. I'll put a couple of targets into the make file, so let's try the first one out. It's called test OTEL. So I'm just going to run that. Okay, looking at how test OTEL works, it's going to use the OTEL environment, which is set at the top of the makefile. So OTEL environment sets a service name, some resource attributes, then an OTEL exporter OLTP endpoint, and that's pointing towards the NewRelic endpoint. Then we've got some OTEL exporter OLTP keys, and inside there you can see it's taking my API key from the NewRelic API key environment variable. A couple of other settings. The first is the attribute value length limit, set at 4095, and the OLTP compression format set to gzip. We're stating that the protocol that the OTEL code's going to talk to the back end is through HTTP protobuf. So the OTEL environment variables that I've just walked through, they're all used by any of the libraries that the OTEL consortium provide. So we're going to use the Go library, but if you were to use another language, exactly the same environment variables are used. And also, luckily for us, the OTEL CLI tool also uses the same standard set of environment variables. So this is great. You learn one set of variables, they use right across the range. So test OTEL sets the environment variables, runs the exec subcommand, setting the service to be makefile, setting the name to be test OTEL, which matches our target, and then the command it's going to run is sleep1. So I did that just to inject a little bit of delay in what's happening. Okay, that's run. So let's now go and look at what's happening inside NewRelic. So where we're going to go is we're going to go to traces. And you'll see by default it'll pick up all traces since 30 minutes ago. And we can see our trace here. Now if your trace hasn't quite turned up yet, that's fine. Sometimes there's a bit of a delay in the back end processing the traces that have been sent to it. So assuming it's there, let's click on it and have a look at some of the information in it. Okay, so it's grouped the traces together. These are all the test OTEL traces. There would be a list of them if there were more than one. So it tells us the trace name, its color on the plot. Where are we? So you can see it's just up there. Happened 4 minutes ago. It took 1001 milliseconds, so just over a second. One entry, one span, no errors. And we can drill down into that particular trace and get a little bit more information. Okay, so up here it tells us there's trace details and there's no logs associated with it. Later on, we'll see where we can add logs into our application and they can actually be linked to the trace. So you can see here's a trace, kind of a duration of what happened. Here's the logs related to it. Okay, we can get some information by clicking on that. And it gives us a little bit of information about what's happened. So it took 1 second, thereabouts. You see some histograms, some nice graphs of average duration, throughput and span duration histograms. Not very useful when you've only got a sample size of 1. Then we can look at the attributes. And this harks back to some of those environment variables we set at the start. So you can see that the deployment environment is code space. That was something that we set as an OTEL environment variable. The entity name is Beaker, matching our project. Where's another one? So the name, test OTEL, and so on and so forth. Here's the command that was run, sleep, here's the command and arguments, etc. And there's a lot of metadata that's captured. So we can see in there, here's a trace, here's what it looks like. You'll notice when we look at the attributes of our trace, there's a bunch of names in there. And it's important to note that OpenTelemetry provides some semantic conventions for those names. I'm going to put a link in the chat which points you to where those names are defined. So this is a list that's constantly evolving. There's a whole bunch of groupings that the OpenTelemetry people have decided to help you organize your trace attributes. So there might be so they're split into things like maybe HTTP attributes, database attributes, cloud events, CI/CD, and so on and so forth. And generally, when you pick up a library, there'll be a set of constants that you can use and make sure that you are getting the right names without having to type them in yourself. Okay, now we're going to run the test OTEL error makefile target. This is kind of very similar to the other one, but we're going to simulate an error happening. So the way that the OTEL CLI works is if you run a command and it returns a non-zero exit code, it'll mark that trace that surrounds it as having an error. So let's run that now. Make test OTEL error, and all it does is you can see it runs the false command. False is always returned an error code. And now let's see what that looks like over inside NewRelic. Okay, I've refreshed the page, and now we can see there's another trace group, test OTEL error, which has got a trace in it. The important thing to note here is now it's showing an error in the error column. So let's dive into that and see how it looks. Okay, we can see one, it's got a nice red sort of highlight to draw our attention to the fact that this trace has got an error. And if we click into that, we can see in the spans, it's highlighting the span because it's got an error in red, which is kind of useful. And we can see in here, we can get some details. Here you go, the status code was error, it exited status 1, it's got an error, and the same kind of attributes and details are available. So as you can see, the back end of these OTEL collectors distinguish between errors and non-errors. So that's a bit of a clue as to what we can do to find things later when we can see if our system's not running correctly, or if we want to find and diagnose problems. When we create traces and spans, we can attach attributes, which are these user-defined data that's attached to the span and captures extra meaning. OTEL publishes these semantic conventions. And there's a Go library which has hundreds of methods that help you follow the correct naming conventions. For example, if you want to follow the convention for setting your service name, you'd go and find the appropriate service name function that'll give you the right attribute name. Now, like other parts of our system, following the conventions established by the OTEL standard means that our system are going to work with a wide variety of tools. If we follow the standard, we're more likely to work with other tools. Next, I'm going to actually run our Beaker service and examine some traces. Now, I know we haven't looked at the code that does that yet, but we'll get into that in the next video. For now, what's important is for us to see the mapping between an API call and response and a trace. So what we're going to do is we're going to run our service, then we're going to run makefile targets that use the NATS CLI tool to exercise the endpoints in our system. They'll all authenticate as a standard caller, send a request and capture the response, formatting it nicely through the JQ tool so that we can see the output in color. It's easier for us to read. So first thing we need to do is type make run to start our API server in one terminal. Then in a new terminal, we're going to run make test get to call the stock get endpoint. Let's do that now. Okay, that's going to build our service and run it. Give that a few seconds to start up. Okay, after a few seconds, it's run up our service and we can see our last message, beaker is running. When we run the make test get command, that runs the target. It's going to send a request. Using the NATS tool, it's going to send a request, translate the output through JQ, and it's going to send it to the stock get endpoint, and it's going to pass a payload which has got a product SKU, and in our case we're going to look at the product coffee cup. Tells us it sent the request, received the reply in about 320 milliseconds, and you can see we're getting this trace parent value. We'll talk about that soon. Okay, here's the reply. So it's okay, true, there's the product SKU, and there's our quantity. And then it does the same call, but for a different product SKU, the coaster. Took around about the same time, and we get a similar result. So let's open NewRelic and find that trace using the trace parent value. So we just go to the traces page, click up on here, trace ID equals, and then we can paste in the value. Awesome. So that's found our trace. Let's have a look at that. Okay, so for a newcomer that opens up this trace, immediately they can see from the entity map that we've got the beaker application and we've got Postgres. So we can see there's some kind of interaction happening there. Down below, we've got all the spans that make up this trace. You can see here there are 12. So let's click on them and let's start having a look at what's going on inside there. We're also going to click on this one that says show in process spans. So that shows the things that are happening inside the method where we've put tracing around it. Click on that and let's see what's happening. So first of all, we've got a validate JSON call, which has taken about 0.38 of a millisecond. Then inside the setup DB con, that's creating our database connection, we can see inside that it's got two child spans. One is pool.acquire, and the other one's a query begin. And then you can see there's some uninstrumented time. But overall, that takes about 0.7 of a millisecond. So it's getting our database connection, getting things ready. Next, we've got some uninstrumented time. That's just time that hasn't been covered specifically by a span. Next, we get stock. That span's got some child spans. So it's got a query, and we can see in here that our traces, it's captured the SQL query that's running. So that SQL query took about 1.47 milliseconds. That's pretty quick. Okay, after the query's run, you can see there's a prepare inside there. That's obviously part of some database internal processing. After the get stop finishes, we decode the request. That takes a very short amount of time, 0.02 milliseconds. Then we've got a transaction commit. That's committing any changes that have been made to the database. Again, almost 0.3 of a millisecond. Then we've got some uninstrumented time. Then we build the response. So that's turning the kind of Go structures into JSON for returning. And our responding in JSON takes 0.09 of a millisecond. So there we go. Overall, our stock get, we've got a trace duration of around 3.2 milliseconds. So what does this trace tell us? The server-side processing for this request response is around about 3 to 4 milliseconds. That's pretty quick. We also know there's no errors, and about half of that time is spent doing the database operations. But hang on, from the client's perspective, it took 320 approximate milliseconds. What's going on? Where's that extra time coming from? It's not on our server, so where's it going? So all that time is spent doing the following. First of all, the NATS client that's running on our code space has to establish a TCP connection with the Synadia NATS global service endpoint. Then the NATS that's running inside Synadia has to authenticate and authorize the caller. Next, that message is routed inside NATS and it's picked up by our service that's also listening to the Synadia cloud instance. So there's a lot of stuff that happens there. Now the request is there. We take about 3 and a bit milliseconds and the response has to go all the way back. Just remember, our client that we're running on, that we issued the API request from, and our API server are both running inside our code space environment, but they go through the NATS system. Now, if we're running them in a production environment, we get way better performance. So we'd be running our API server on a cloud system, maybe AWS or something like that. It's not going to be running in the code space. We'd also be running a separate OTEL collector. So our application wouldn't have the burden of kind of managing and filtering all of the traces and logs and other metric information. Also, remember, our database is just, again, another one that's running inside Docker on our code space. In a production environment, that'll be a high performance dedicated Postgres server. And then this particular test establishes a connection and breaks it down at the end. So in a real world scenario, you're more likely to be using a long running connection. So the cost of actually establishing the TCP connection, performing all the TLS negotiation, doing all the authentication and authorization will be amortized across many API calls. In a real production environment, I'd be expecting to get around 10 milliseconds responses for something like this. Easy. Okay, great. So now we've got some basic information about our API calls. Back to our analogy of the patient in the hospital. By regularly looking at the traces, we can see how our system's performing over time. But what we really want is immediate action when some important event occurs, i.e., in the hospital scenario, that might be an alarm going off. In our context, a few critical errors can occur. One scenario might be when our system has an error, which we simulated with our test OTEL error makefile target. In this case, we definitely would want NewRelic to alert us when traces come through that have been marked as error. So these systems like NewRelic have integrations that will allow you and your team to receive events through email or Slack or some other communication tool. Some of them might even open tickets for you and make them visible in your ticketing system like Jira. The other example might be a requirement from your business users. It might be of great interest to them if you're running an inventory system like Beaker when a stock level falls below some sort of threshold, because that would be the trigger for some business process where they need to get some more stock in. One option is you could handle that by recording the stock level as a metric using OpenTelemetry. Now that's a different part of OpenTelemetry I'm not going to go into with this series, but there's plenty of information online. Another option is that our application could deliver its own feed of messages when this happens. In fact, that's exactly what we're going to do, and we'll show that in a later video. When the stock remove endpoint's called, stock falls below a threshold of 10, we publish a message to NATS. I'm just pointing this out to indicate that telemetry isn't the only way for our system to notify adjacent systems of changes. In fact, this technique of publishing a message is really powerful for building loosely connected apps that react to changes in real time. But that's a topic for another time. Okay, so that wraps up our telemetry discussion. Thanks for listening. And remember, iron sharpens iron and one man sharpens another. Hit the subscribe button if you want to be notified when the next video is out. In the next video of the series, we'll finally be getting into the guts of our microservice. We're going to pull all these threads together that we've been learning about and we're going to show you how we implement the API handlers. I'm really looking forward to it. See you then.